Okay, hello. We are ready now for Chapter 3, titled Understanding Vehicle Space Needs, Natural Laws, and Balance. The controls: accelerating, braking, and steering. The controls. As a driver, you control the speed and placement of a vehicle through three main input channels: accelerator, brakes, and the steering wheel. Each of these controls is easy to operate, but smooth, coordinated use is developed with practice. Practice will help you become more familiar with the differences in the feel of the vehicle you drive. It will also help you notice how your body and the vehicle react to abrupt braking, steering, and acceleration compared to smooth operation of the same controls. Remember that smooth operation of brakes, accelerator, and steering depend on proper adjustment of the seat and steering wheel, as well as an upright position behind the steering wheel as described in Chapter 2. Visual input. Few people appreciate the degree to which attention to driving and the directed visual search influence their chance of being involved in a crash. It is important to remember that the eyes see what the brain directs them to look for. When driving, you should be searching for objects or conditions within, along, or closing on your planned path of travel. To operate a vehicle smoothly and safely, you must develop the habit of directing your attention 20 to 30 seconds ahead and to both sides along your intended path of travel. This will allow you to identify objects or conditions that could increase the level of risk. Relating to other objects. Just as important as developing smooth control of steering, braking, and accelerating is knowing your vehicle's placement in reference to other objects on and off the road. You should be able to determine whether you can safely move into a planned space ahead, to the other side, or to the rear of your vehicle. Vehicle operating space. Operating space. At all times, you will need adequate operating space in front of, to the sides of, and to the rear of your vehicle. It is important to maintain open space in these areas so that you can move the vehicle there if necessary. Operating space can be thought of as a space cushion, extending in each direction from the vehicle. The need for space. As speed increases, the operating space required also increases, especially space to the front of the vehicle. As you travel faster, having additional space will allow you more time to respond to a situation. Miscalculating space. If you incorrectly judge the amount of space needed to operate a vehicle in a given situation, the possible outcomes range from a minor fender bender to a destroyed vehicle with potential for serious injury. Adjustments in speed and position must be made in direct proportion to your operating space requirements. Targeting line of sight, planned path of travel. Planned path of travel. To allow enough distance to stop in response to threatening objects or condition, you must identify a planned path of travel or visual control zone 12 to 15 seconds ahead. An alternate path into which the vehicle can be steered if the planned path of travel is blocked must also be identified. Under most conditions, a following interval of 3 to 4 seconds will enable you to adjust speed or position appropriately. However, 3 to 4 seconds may prove insufficient if the alternate path involves leaving a paved roadway or braking to a stop on the shoulder. Under such conditions, it is critical that you be aware of any vehicle to the rear, including its size, lane position, and distance behind. Referencing vehicle to path of travel. Visual referencing. A visual reference, a visual reference point relates some part of the roadway to some part of the vehicle. Good space judgment depends on your ability to visualize space, accurate visual referencing, knowledge of space needs, and driving experience. Experience and visual referencing are the most important factors in developing good space judgment. Each driver may see the relationship of roadway surface to the vehicle somewhat differently, depending upon the position of the driver's body, the driver's size, and the vehicle type. Variables that can influence perception of reference points are eye dominance, seat adjustment, seat height, head movement, and the type of vehicle. The visual reference points, however, will be similar for any vehicle. Road surface and traction. Traction. Traction is the adhesion, friction, or grip between the tires and the road surface. Without traction, a driver cannot steer, brake, or accelerate. A loss of traction may cause a loss of control that can result in skidding. Traction variables. Traction varies with the vehicle's speed, tire condition, and road surface. As a driver, you control your vehicle's speed and the condition of your tires. However, you have no control over the road surface or its condition. So you must learn to recognize conditions that may indicate a change in traction, which in turn will require a change in speed or direction. Surface material. Road surfaces produce different amounts of traction. The following are ranked in order from the greatest traction to the least. Number 1, concrete. Number 2, asphalt. 3, brick or polished concrete. 4 is dirt. 5, gravel. 6, sand over hard surface. Conditions that can affect traction: surface materials, substances on the road, surface conditions, roadway design. Substances on the road. Any substance on the road surface can reduce traction. Be alert for sewer covers, paint, vinyl strips, tar, wet leaves, sand, loose gravel, or mud. These substances will almost always produce the level of adhesion or traction. I'm sorry, these substances will almost always reduce the level of adhesion or traction available. Sand spread over an icy road is an obvious exception. Oil, tar, radiator overflow, and rubber left by frequent vehicle starts and stops at intersections all have an adverse effect on adhesion. Surface conditions. Poor road conditions, such as rippled surfaces or potholes, can contribute to a loss of traction. Be especially alert when the road is wet. At the beginning of a rainstorm, dirt and oil can rise and mix on the roadway surface, making the road extremely slippery. At speeds as low as 35 miles an hour and a water depth of only 1/12 inch, hydroplaning can occur. This action, similar to the phenomenon that makes water skiing possible, occurs when the tires rise up on a wedge of water. Your speed, tire inflation, width, tread, and the depth of water on the road all influence the speed at which a vehicle will hydroplane. In all situations, it is the driver's responsibility to prevent his or her vehicle from hydroplaning. Temperature changes. As temperatures rise from below freezing to about 32 degrees, icy and snow-packed areas become more slippery. Wet ice is much more slippery than dry ice. Intersections are likely to be slicker because starting and stopping vehicles polish the ice. Other factors. In addition, bridge surfaces, overpasses, and shaded areas may freeze before other road surfaces. Wind gusts and strong crosswinds can make steering on a slick surface difficult. Large buildings or embankments may block the wind, cause a sudden change in wind direction, or shade an icy area from the sun. Patches of ice or wet leaves can cause unequal traction. Under such conditions, even moderate braking or acceleration may result in loss of traction that can lead to a sudden skid. Road design. Roadway design features such as banked or crowned roads can have an effect on traction and control. A crowned roadway is a road that is higher in the middle than at the sides. A banked roadway, usually found at a curve, is higher on one edge than the other. Here are some examples of roadway design that can affect traction. Again, crown roadway, uneven shoulder, or banked roadway. Shoulders. Roadway shoulders frequently provide the only escape path in an emergency. However, the shoulders of most highways provide less traction than the road surface. As a result, you need to be aware of shoulder conditions whenever you drive. Shoulders may be rough or soft, covered with loose materials such as dirt, cinders, or sand, or littered with broken glass or other waste. When steering off the road onto the shoulder, expect a reduction in traction. Braking with two wheels on the road and two wheels on the shoulder will result in unequal traction and may cause skidding. Shoulders may not be even with the road surface. A common problem is that roadway shoulders are not even with the road surface. In such cases, particularly where the difference in the surface level is 3 inches or more, extreme caution is advised. A driver trying to steer a vehicle back onto the road may scrub the inside wall of the front tire on the edge of the road, resulting in steering problems or loss of control. Natural laws and traction. Inertia. Traction also is affected by inertia. Simply stated, an object in motion continues to move straight ahead until acted upon by some outside force. This force creates problems when a driver changes a vehicle's direction too suddenly. As the car travels around the corner, inertia tends to keep the car moving forward in a straight line, rather than allowing the car to follow the curve or turn. Unless traction is great enough to overcome the force of inertia, the car will slide to the outside of the curve or turn. 5 factors influence the effect of inertia. 1. Sharpness of the turn or curve. 2 is speed. 3. Size, height, weight, and load of the vehicle. 4. Roadway slope. And 5. Roadway surface condition. Gravity. Gravity, the invisible force that keeps our feet on the ground, also affects vehicle traction and performance. Gravity's downhill pull affects a vehicle's ability to accelerate and maintain speed on hills. When going uphill, you must accelerate to keep a constant speed and overcome the force of gravity. On a slippery hill, acceleration may result in a loss of traction. Driving downhill. Conversely, when you drive down a hill, the force of gravity tends to boost speed, which increases the stopping distance. A crown road that curves sharply right or left can be especially dangerous if located on a downgrade. On such a road, traction must overcome both the force of gravity and inertia. Kinetic energy. Movement requires energy, and the faster an object moves, the more energy is needed. Kinetic energy, the amount of energy needed to propel a vehicle, is affected by the vehicle's weight and speed. Kinetic energy also directly relates to decelerating a vehicle. First, braking distances needed to stop a vehicle increase by the square of the amount the speed is increased. For example, if a vehicle speed doubles from 20 miles per hour to 40 miles per hour, the distance needed to stop increases by 4. Second, the force of impact in a collision also increases by the same ratio, the square of the increase in speed. That means that if a vehicle's speed is doubled, the forces involved in a collision will be quadrupled. Braking distances needed to stop a vehicle increase by the square of the amount the speed is increased. For example, if a vehicle's speed doubles from 20 miles per hour to 40 miles per hour, the distance needed to stop the vehicle increases by 4 times. Very important. Vehicle suspension, braking, balance and traction. Single vehicle crashes. More than 50% of occupant fatalities occur in, as a result of single vehicle crashes. Basically, the vehicle leaves the roadway and strikes a fixed object or overturns. Almost without exception, these crashes involve improper steering or braking or a combination of the two. Improper steering or braking or both can upset a vehicle's balance, which can lead to a loss in traction and an unintended path of travel. Matter of balance. Vehicle suspension balance refers to the distribution of weight of the vehicle on the chassis. A transfer of weight from one point of the vehicle to another occurs whenever the driver accelerates, brakes, turns, or performs some combination of these actions. The amount of weight change and the driver's ability to control the vehicle are influenced by the rate of acceleration, brake application, steering input, surface traction, or combinations of these factors. Weight distribution. The vehicle's weight can be shifted from the center of the chassis, with the weight distributed approximately equal over the front and rear tires, to a position where weight is concentrated over the front, rear, left, or right tires. When the vehicle is stopped or traveling straight at a constant speed, its suspension and traction are stabilized. Again, when the weight is transferred to or away from a tire, the size of its contact patch will change. A tire's contact patch is the amount of tire rubber that is in contact with a pavement at any time. The larger a tire's contact patch, the more traction that tire has on the road surface. The average size of a tire's contact patch is approximately equal to the surface area of an adult human palm. Changing vehicle suspension load, front to rear. When a vehicle accelerates, its weight shifts to the rear. The rear suspension compresses, and the rear tires contact patches increase in size. while the front tire's contact patches decrease in size. If acceleration is aggressive, there will be a noticeable rise of the vehicle's front and the drop of the rear. The table on the next page summarizes the effects of acceleration, braking, and steering weight transfer and the tire contact patches. Changing vehicle suspension load rear to front. When the brakes are applied, the vehicle's weight or center of mass is transferred to the front. If braking is hard, there is a noticeable drop in the vehicle's front and a rise of the rear. Occupants will feel forward movement. Apply too little brake pressure and the vehicle will not stop at the desired point or within the distance available. Apply too much pressure and the vehicle wheels may lock up, resulting in loss of traction and directional control. Changing vehicle suspension load side to side. When turning, a vehicle's weight will shift in the direction opposite the turn. For example, when turning right, the vehicle's weight will shift to the left, causing the vehicle to lean to the left. The degree of weight shift depends on speed, traction, and the amount of speed of steering input. Maximizing traction. To maximize traction and minimize the chance of traction loss, avoid sudden inputs when accelerating, braking, or steering. For example, applying the brakes when cornering too fast will slow the vehicle very little and may cause a skid because of severe weight shift. Also, focus on executing one input at a time. Brake, then steer, then accelerate. Performing smooth inputs one at a time will help maintain maximum traction. Seating position. To most effectively control vehicle balance, drivers should sit in a comfortable upright position directly behind the steering wheel. This will also help maximize the driver's view of the driving environment.